We are using FPGAs for spectrum sensing and modulation recognition. I'm Ryan.
Hi, I am Zhuohuan Li.
I'm Simon Dime.
And I'm Jacob Marin.
A little background. Here I will explain a few terms that will be used throughout this presentation. Modulation scheme. This is the language that the device speaks. This will tell us how a device communicates. IQ data. These are the noises coming out of the device's mouth. Putting these noises together in a controlled fashion makes a language. Putting IQ samples together in a controlled fashion makes a modulation scheme. SDRs, or software-defined radios. These are the ears that hear the noises. An SDR will listen to the radio environment and jot down what it hears as IQ data. FPGA, or Field Programmable Gate Array. Most wireless devices have very specific hardware that allows them to communicate. Regular computers can approximate the performance of this hardware, but FPGAs can do this better.
The goal of our project is to use machine learning to recognize different wireless devices under an environment by processing the signals transmitted by them. By using the software-defined radios, which we introduced before, we can record the IQ samples from different wireless devices, such as phones, Bluetooth, earbuds, laptops, and also Wi-Fi environment. All the data we collected from software-defined radios will be used as training data to a set of neural networks and also classify them based on their different modulation scheme. Furthermore, we will construct a matched filter implemented in FPGAs to compare the performance against the machine learning-based modulation recognition.
Data collection. Our goal is to mimic wireless transmissions in a mostly controlled environment to be used later as training data for a modulation recognition neural network. For physical transmitting and receiving, we use the USRP X310 and B210 SDRs that are attached to the orbit grid. To generate the Wi-Fi IQ samples, we use the Wireless Toolbox library in MATLAB. To transmit and receive the IQ samples at the software level, we use the UHD sample scripts. We also used OEDL to manage all of the devices in this experiment. The experiment. To the left, you will see some properties of our experiment. If you look to the right, you will see the orbit grid, which is a collection of devices at WinLab used for experimentation. Each square with an X on it indicates a device that we are using. The green lines indicate the distances between the nodes used in this experiment. Data collection flow. First, we will copy the Wi-Fi IQ sample files from the central node to the transmitter nodes. Next, we will transmit the Wi-Fi IQ sample files via USRP to the receiver nodes. And if you look in the middle of step 2, you will see a cloud that represents real-world noise. Running this device on the grid gives us the benefit of real-world interference from other Wi-Fi devices. Using real noise in our data makes our neural network more resilient. In other words, it will be better at distinguishing between modulation schemes when there is noise involved. And for the final step, we copy the received Wi-Fi IQ sample files to archival storage.
For matched filters, a matched filter is easy to understand. For example, we use water filter to clean the water we drink by eliminating the impurity. Here, the matched filter has the same function, but it's for the radio signals. In signal processing, we use it to filter the noise which is meaningless or unwanted from the signal we received, just like purifying the water. So for technical parts, what it really is, it's like a process to detect whether a particular piece of known signal exists in an unknown and noisy signal we received, and check if the output of the filter is the same as our template signal. It can also show us if the unknown signals we received matches with the modulation scheme provided locally. So for us, we have different type-based modulation recognition. The first one is neural network-based modulation recognition, and the feature of it is it requires little prior information and can be used for the signal we don't even know. The second one is matched filter-based. It requires more information and need to be used on the signals we have seen before. So we need to compare the performance of two different type-based methods and make sure that the performance of the neural network is at least comparable to that of the matched filter for signals we know some information about.
So we represent the signals in this project with pseudo-random numbers. To generate these sequences, we made a linear feedback shift register in the programming language Golang. This is an algorithm that creates the random data by taking input values and generating bit sequences that are combinations of zeros and ones. As you can see, the pictures to the right are example outputs for the starting values 99 and 100. And since these bit sequences vary on the input, each signal has its own sequence attributed to it. This is important because then we can use a matched filter to search for bit patterns in these sequences and help us determine the signals.
So as for our future goals for this project, one of them is using a match filter to identify the modulation schemes for random sequences. So the way this would work is we would generate random data using the linear feedback shift register that Jacob talked about. And this would be a very long string of randomized bits consisting of zeros and ones, as shown here. Then what we do is create a specific 8-bit sequence in modulation to use as a match filter, so as shown here. And essentially what we would do afterwards is traverse the random data and use the match filter to find hits within the random data string. And our hope is to eventually be able to use multiple sequences as match filters at the same time to increase the speed of hit detection. And this ties into another future goal of ours, which is using match filters in conjunction with neural net data and FPGAs to classify devices. So right now we are currently using MATLAB to develop the match filters because we have access to many built-in signal processing functions and libraries within MATLAB, and it's easier for us to compare the results of using match filters versus machine learning, which is one of our goals. And then from there, what we want to do is transition to using Go, which is another higher level programming language. And we want to use Go is because its use of Go routines and channels would allow our programs to run in parallel and run much faster. And this would be beneficial to us, especially if we want to use multiple filters concurrently. And then finally, what we want to do is compile our Go filters into Verilog, which is another language via a Go to Verilog compiler. Because Verilog is used to run on FPGAs, which is the namesake of our project. And from there, we would want to use the FPGAs to detect RF signals of various devices. Any questions?